Welcome back to The Explainer. Today we are tackling something truly mind-bending and honestly incredibly exciting. We're going to take the seemingly intimidating mathematics of artificial intelligence and translate them into intuitive, digestible building blocks. We're getting right under the hood to see how these massive systems actually work. You know, as the author of our source text notes right at the beginning, there is a certain comfort in mystery. And it's so true, right? It's incredibly tempting to look at AI's sudden explosive capabilities, like models out of nowhere knowing how to write complex code or translate completely obscure languages, and just view it as pure magic. I mean, it literally feels like magic. But we aren't here to settle for magic today. We're here for a better, clearer explanation. Okay, let's dive into this. Our roadmap today comes directly from a brilliant deep dive essay in Tech Reader magazine by Aaron Rose, titled The Math Behind the Magic. He breaks down 4 distinct mathematical frameworks that explain how ChatGPT was really built, and he validates the hard science behind all these surprises. We're going to visualize this together so you can actually grasp the mechanics of how this stuff emerges. Here is our agenda for today. We'll start with the mystery of AI emergence, then move through 4 scientific pillars: scaling laws, phase transitions, the information bottleneck, and representation geometry, before wrapping up by decoding the magic. Starting with Section 1, the mystery of AI emergence and capabilities appearing from out of nowhere. So here's the core problem we're solving today. Massive language models suddenly developed abilities that nobody explicitly trained them to have. They literally surprised their own creators. But instead of just leaving that as some seductive mystery, we're going to replace it with 4 grounded scientific frameworks. We're moving from just observing the model from the outside straight into the internal mathematical mind of the AI. Section 2. Scaling laws, predictable growth, and turning AI development into actual engineering. Our first pillar takes us back to 2020 at OpenAI. Researchers published a paper discovering what we now call a neural scaling law. Simply put, this is a precise, quantifiable mathematical relationship, specifically a power law between a model size and its performance. Now, don't let the math intimidate you here. This mirrors the exact same patterns we find in things like earthquake magnitudes or even how city populations grow. At its core, this law reveals something brilliantly straightforward. As you make the model larger, as you increase the number of parameters, the loss, or the error rate, decreases. The model simply gets better. This single equation was a total game changer. It transformed AI from a massive, risky gamble into a forecastable science. It gave developers the absolute confidence to invest billions in simply scaling these things up. But here's where it gets absolutely fascinating. Because while this law allowed researchers to optimize their compute budgets and forecast capabilities with a curve that fit the experimental data beautifully, it also revealed something totally unexpected. There were these mysterious kinks in the curve, sudden places where the rate of improvement just shifted qualitatively. And that first law, it couldn't explain those kinks at all. Which brings us to Section 3, phase transitions, the threshold, and the mathematics of sudden shifts. To figure out what those mysterious kinks were, researchers had to borrow from statistical physics. Enter our second pillar, phase transitions. Think about water freezing into ice, or maybe a magnet losing its magnetism when it gets heated up. The underlying physics are completely continuous, but the observable, macroscopic behavior changes suddenly and discretely. Translated into plain English, this threshold function is startlingly simple. Below a certain scale, the model's capability is 0. Above that critical scale, it exists. It's a hard threshold. Nothing, 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 then something. And this perfectly mapped onto the behavior they were seeing in those GPT scaling experiments. It isn't a slow, gradual rise in ability, it's an abrupt, sudden transition. To really visualize this, think of a child learning to read. The child's brain is continuously building these complex neural pathways for months. That's the continuous underlying physics. But the observable behavior, that moment the kid actually starts reading words out loud, feels incredibly sudden. It's the exact same concept here. The AI model is continuously improving underneath, but the new capability only surfaces when it crosses that critical mathematical threshold. Section 4, information bottleneck, compressing language, and the mechanism of abstraction. So while phase transitions give us the shape of emergence, we actually still need Claude Shannon's 1940s information theory to explain the mechanism behind it. We call this the information bottleneck. It turns out a large language model isn't just some fancy prediction machine.
It is a highly sophisticated compression machine, balancing a very delicate mathematical tension. Essentially, this third equation forces the AI to balance two completely opposing goals. It has to minimize its errors while simultaneously minimizing how much raw data it actually holds onto. Now, the model doesn't consciously know it's solving an information bottleneck problem, but the math proves that it is. It's constantly walking this tightrope between retaining data and compressing it.
You can actually see this delicate tension play out in stages. Look, if the model retains absolutely everything, it's just pure memorization. No actual learning or generalization is happening. If it compresses too aggressively, it destroys its accuracy completely. But by navigating this tension perfectly during training, something amazing happens. It stops memorizing surface-level patterns and is forced to uncover deep, latent structural abstractions. It starts fundamentally understanding the generative structure of human language. Moving to Section 5, Representation Geometry, Drawing Boundaries and the Shape of the Model's Mind. This brings us to our final and honestly most concrete pillar. What does all of this deep abstraction actually look like inside the AI? It looks like geometric separability. Every single model converts tokens of text into vectors, which are basically huge lists of numbers, in a high-dimensional mathematical space. The geometry of how these vectors are arranged literally encodes everything the model knows. Ultimately, the math reveals this. A capability exists when that internal geometry organizes enough to allow a clean boundary. So that spooky, emergent behavior we talked about at the start, it isn't magic. It's just the model finally drawing a new topological line in its mathematical brain. It's geometrically separating concepts, like putting vectors for formal text on one side of a line and informal text on the other. Notice the stark difference here before and after emergence. Beforehand, the vectors are all scattered and mixed up, and the model completely fails the benchmark task. But after emergence, after it crosses that phase transition and compresses the data enough, the vectors are cleanly separated. A clean boundary can be drawn, and boom, the capability is suddenly reliably there.
Section 6. Decoding the magic. It is not magic, folks. It is topology.
So the absolutely crucial takeaway here is how all four of these distinct frameworks synthesize into one coherent story of how ChatGPT was truly built. Scaling laws justified the massive computational investment. Phase transitions explain exactly why the capabilities jumped so suddenly. Information bottlenecks forced the model into deep abstraction, and representation geometry is what actually drew the boundaries to make those capabilities accessible. We might not perfectly predict exactly which new trick an AI will learn next, but we absolutely understand the structural math behind how it learns it. Which leaves us with this final, provocative thought to chew on. As these models continue to scale exponentially, right now, in labs all over the world, what latent capabilities are currently organizing beneath the surface, just waiting to cross the next mathematical phase transition? Just think about the implications of that geometry. Thank you so much for focusing in and exploring this explainer with me today. Keep learning, and I'll catch you next time.